This is 1-2 properties of real numbers. Real numbers, remember that, I guess, much later from now. But yeah, we're talking about numbers that are real. And so a lot of this is probably, or maybe all of it, is probably going to be a review from Algebra 1 or whenever. Subsets of real numbers. And again, all these numbers below are in fact real. There's the natural numbers. Perhaps you remember what the natural numbers are. What are the natural numbers? Well, the natural numbers have a different name or a secondary name, the counting numbers. So the natural numbers can also be called the counting numbers because they are the numbers you use to count things. You know, you would count something, 1, 2, 3, 4, 5, 6, 7, 8, and whatever. That is how you count. So the counting numbers are all of these numbers going off basically endlessly. Again, 7, 8, 9, etc. Then there's the whole numbers. Do you remember what the whole numbers are? Well, essentially, if you toss 0 in with the natural numbers, that's the whole numbers. So the whole numbers start off with 0 and then go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and off forever in that direction. And then we can say the integers. Do you remember what the integers include? Well, the integers, some people say they are the whole numbers and their opposites. But I guess in this lesson, saying the word opposite is getting a little, ahead of ourselves, a little premature. But here's what the integers are. You could go like -2, -3, -4, -5, -6, -7, -8. And if you keep that pattern going in that direction, and then also in the positive direction, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and in that direction forever. So those are all the integers, or the nice numbers, I guess you could say, quote unquote, nice numbers. So it also includes the negatives, the negative nice numbers. There's also these things called the rational numbers. That's a subset of all the real numbers. And do you remember what rational numbers are? What makes a number rational? Numbers that can be written as a quotient of two integers. In other words, like what do you basically call a quotient of two integers? You can call that a fraction. Now that is basically that's like the official definition of a rational number. A number that can be written as a fraction, basically, as a quotient of two integers. But there's a more of a maybe unofficial, perhaps easier way to remember what rational numbers are and what they're all about. So here it is. Basically, they are numbers with what or what decimals. How can you describe the decimals of a number that's rational? Well, it's terminating, which means it ends, it terminates at some point, or repeating. So the decimal has to terminate at some point, or it can actually go on forever as long as it repeats itself. It repeats a pattern in the decimal. You know what I mean? like 0.333 forever. In other words, 0.3 repeating. That repeats a pattern, right? And So 0.3 repeating is rational, and you could also prove that by by pointing out that you can write it as a fraction. 0.3 repeating is the fraction 1/3. So here's some questions here that hopefully we can answer very easily. Are the natural numbers included in the rational numbers? So are all these numbers rational? Can you write them as fractions? Do they have decimals that either end or repeat a never-ending pattern? And the answer is yes. Okay? And I'll explain that if I have to, but let's answer these three questions first. Are the whole numbers included in the rationals? Well, I mean, the whole numbers are, they just include 0 from the naturals. So that answer is yes. If a number is a whole number, then by default, by definition basically, it's also rational. Are the integers included in the rational number set? Can you include all of these numbers? Like, is -5 rational? Is -2 rational? Is -50 rational? And, can they be written as fractions? Do they have decimals that either terminate at some point or repeat a pattern? And that answer is yes. And here's a couple examples. See, I knew I'd explain it. So this justifies, basically all these three can be justified, by examples like this, okay? Like 7 is officially rational because you can write it as 7/1. Same with -4. -4 is an integer, but you could also say it's rational because you could write it as -4/1, a quotient of two integers, a fraction. So we also, in contrast to rational numbers, we also have numbers that are irrational. And it's kind of the opposite. I don't like to use that word lightly in math class, but it's pretty much the opposite of rational, right? Just like in your everyday English language, right? So whereas rational numbers are like this, characterized by this kind of stuff, with an irrational number are numbers that cannot be written as a fraction. So if a number cannot be written as a fraction, it has to be using integers, right? Nice numbers making your fraction. If it cannot be written as a fraction, that's a big time, that's big time evidence that it's irrational. And basically, I'll skip ahead here. The decimals of irrational numbers, again, like if these are how the decimals act with rational numbers, that means if a number is irrational, that means it has a decimal that would what? Wouldn't it have to go on forever and yet never repeat a pattern, like almost go off forever randomly? So the decimals of irrational numbers never end and they never repeat a pattern. They're just crazy. They're irrational. The word irrational is a pretty good name, because of how the decimals act. They're just crazy, random, irrational, out of control, no pattern, and it goes off forever. So one example of an irrational number is the square root of 2, right? Check on your calculator. It'd be a decent way of analyzing the square root of 2. Just go on your calculator, make sure it's in like a classic sort of mode where it's going to give you a decimal, when you enter it in, and you'll see what I mean. Like the square root of 2 is like 1.41, blah, it goes off forever. And there's no pattern to the decimals. It's just kind of random. Yeah, like I just said, take a look at the decimal representation. What do you see? I just kind of said what you're going to see. Other examples of irrational numbers. Can you think of any other ones? Well, pi, maybe you thought of pi. Pi is an irrational number. Remember, like 3.1415, yada, 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 it goes off forever. So yeah, don't forget that pi is an irrational number. We use this symbol, but it's a number. It's an irrational number, but it's a number. And we also have, again, speaking of, let's lock that down. Lock it down. Lock it all down. So, speaking of premature a few minutes ago and getting way ahead of ourselves, but, here's another just quick example. This number that we just refer to as e, the natural exponential or Euler's number, whatever. But you'll learn eventually, like in pre-calculus, all about this number. But it's just a number, and it's another example of an irrational number, kind of like pi. We use a symbol for it, but you don't need to be aware. Just again, full disclosure and everything. You don't need to know about this number yet. Again, this is just merely a random example of an irrational number that you'll work a lot with in pre-calculus class. And other examples are like other square roots. Square roots are actually probably the main example of irrational numbers. The square root of 2, the square root of 10, the square root of 24, the square root of 27, the square root of 305, Not all square roots, though. Can you think of a square root that is not irrational, basically rational? Can you think of any of them? And, a very simple example is the square root of 4. Think about it. What's the square root of 4? The square root of 4 is just 2. It's totally rational. What's the square root of 9? The square root of 64. So there's obviously plenty of examples, an infinite amount of examples actually, of square roots that are actually rational, but, most of them, quote unquote, most of them. It's weird using the word most when there's an infinite number of whatever, but most square roots are irrational. So types of homework or test problems. To which sets of numbers does each number belong? And you can check off more than one box. It's not like we want you to check off the most specific. Like if I wanted to be the most specific for what kind of number is 9, I would say natural. That's being the most specific, talking about the number 9, but 9 is also a whole number. It's also an integer. It's almost like a snowball effect. Because 9 is natural, that automatically makes it whole, which automatically makes it integer, which automatically makes it rational. Remember, these sets live, sort of in each other. There's big time overlap of these these sets of natural whole. Okay. The square root of 3. What descriptions can we use for the natural? No. It's irrational. Just look at the decimal, right? And how we cannot write this as a fraction. -7. It's not natural. It's not whole. It is an integer, and guess what? Since it's an integer, it's also rational. And 41 hundredths, or 0.41. Nope. Is it rational? The decimal ends at some point, so yep. So that is rational and only rational. All right, moving on here. Let's get all, this is not calibrated right now for some reason. Oh well. So observe that 5 plus negative 5 is what? Well, that would be 0. And negative 12 plus 12 would also be 0. And 3.4 plus negative 3.4, you guessed it, 0. And negative 1/2 plus 1/2, 0. Okay? And essentially, what's the punchline here? That the sum of a number and its additive inverse, in other words, like what's the probably the way more common term for additive inverse? It starts with an O. I used it already in this lesson twice, in this video twice. Opposite. So what do you get when you add a number and its opposite? You always get 0. Okay? Now get used to this whole, like, I don't know. I guess here's what I'm getting at. The word inverse, I don't think there's a bigger can of worms when it comes to vocabulary in math, at least high school math, than the word inverse. Okay? You'll probably hear me say this half a dozen times this semester, potentially, but math vocabulary is usually pretty straightforward, sensible. They use pretty good words. Like they don't. It's sort of its own language, but they make it about as easy as they can, and they have pretty good names for things. You know what I mean? And only rarely will you have a vocabulary word in mathematics that can mean different things based on the context, based on what you're doing, right? The word range is one of those words. So be very aware that the word range can mean different things in different situations. The word tangent is another one of those words that has different meanings, right? I feel like there's another one that that I just can't remember right now that I usually have, in my holster, in my back pocket. But the big one is inverse, man. Oh, you have to be really, really careful with the word inverse. There's all kinds of different. I can think of at least 4 right now, but I'm not going to go there. I'm just saying, let's definitely emphasize, the term opposite, the vocabulary word of opposite, rather than additive inverse, at least long term going forward. Like here, in this next series of examples, what's 4 times 1/4? What do you get when you have 4 times a fourth? And maybe you're one of those people that make, writing 4 as 4/1, that like really helps. But the bottom line is you get 1. And when you do 5/2 times 2/5, I don't know how you, again, I could even go back here to talk about this type of thing, but you could talk about how this is like 10/10, or you could like do some canceling even before you multiply the fractions, whatever. But the bottom line is you're going to get 1. And √3 times 1/√3, you get 1. And 1/7 times 7/1, you get 1. And all this is just there to show that the product, which means multiplying, obviously, of a number and its multiplicative inverse. But we're going to go with what word? Like what's the better word? The more specific, unique, I guess, word, exclusive word that describes like 5/2 and 2/5. Like what kind of relationship does 5/2 and 2/5 have? Or 4 and 1/4. It starts with an R. Reciprocals, or as I sometimes say, wait for it, reflipricals. Get it? Flipricals, because you're flipping. Because when you flip 5 over 2, you get 2 over 5. And the bottom line is that whenever you multiply reciprocals together, you get always 1. It's just the way it goes. And hopefully you remember that this right here basically means the absolute value of 12. Which is what? What's the absolute value of 12? Well, it's 12. What's the absolute value of -6? What? That's not right. What in the heck? That is... Who put that there? It's just 6, man. And the absolute value of 23 is 23, and the absolute, this will be, okay. And the absolute value of -5.67 is positive 5.67. Because absolute value, like, makes something positive if it's not already positive. If it's already positive, it doesn't really do anything to the number. But that's not the official definition. Like if you looked in a textbook or on Wikipedia, or if you jumped on your Google machine and you know did a search on like what absolute value is, what would it say? You know, what would a textbook say? Absolute value of a real number is the distance that number is from 0 on the number line. So I guess the key word here is distance, and that's why absolute value is always positive at the end of the day, because it's the distance away from 0 on the good old number line. And to finish this section of notes, a little chart of properties. So real numbers have at least a handful of properties that you should at least kind of be aware of, you know. This is a keystone thing. They will ask you to, you know, like literally name or, like what's the word? You know, identify what property is in play if they show you some math. You know what I mean? Like if they show you like something like this, you know, and they say, what property is this representing? You know what I mean? Then you have to be able to, you know, label that by name as the distributive property. You know what I mean? So this closure property is probably the least important one to spotlight, you know, to highlight. You know, the closure property basically says that, and this is how you say it. Again, I don't want to give this too much time, but what you say is that the real numbers are closed under addition. Let me say that again, because that's just the proper way to say it. The real numbers are closed under addition because if you add two real numbers together, you know, the addition part, if you add them together, you get another real number. So that's what it means to be closed under addition. And the real numbers are also closed under multiplication, because if you multiply two real numbers together, what you get is another real number. You know what I mean? Now, again, I keep dwelling on this, even though it's not that important of a property, at least as far as things like the Keystone exam goes. But, for example, you cannot say that the real numbers... Actually, wait a minute. I want to bite my tongue here for a second. Real numbers are closed under... I mean, I could, no, I'm going to switch this up, have a better example. Let's say the integers, okay? Are the integers closed under addition? If you add two integers together, do you get an integer? And, I'm going to say the answer is yeah. Are the integers closed under multiplication? If you multiply two integers together, will you get an integer as an answer? And I think the answer is yes. But if you talk about, say, the integers being closed under division, are the integers closed? Do you always get another integer if you divide two integers? And the answer is no. So you would not be able to say that the closure property applies to integers under division. But anyway, let's move on to more important properties, like the commutative property. And an example of the commutative property, at least for addition, I'm not gonna just dwell on this forever. But a quick example of the commutative property is like if you do 2 plus 3, isn't that the same as 3 plus 2? It doesn't matter which one you say first with addition or even multiplication, it doesn't matter, right? So that's the commutative property, that these are the same. The associative property is like if you have 2 plus 3 plus 7, right? Does it matter if you add those two together first versus adding those? It doesn't matter. So, this left side is equal. That's the associative property. The identity property of addition basically says that if you add 0 to a number, it's going to maintain its identity. That's why it's called, again, I told you, the math vocabulary uses some very common sense words, some good words. Again, because if you have 5 plus 0, it's going to stay 5. It's going to maintain its identity. Just like any number, if you multiply it by 1, it maintains its identity. So that's why this is the multiplication, property with the identity, or as I should say, the identity property of multiplication. Because multiplying by 1 doesn't change it. It maintains its identity. And then the whole inverse thing, even though I cringe using this word too much, and just because I know it's kind of all over the place, the word inverse, but this is like adding, when you add two opposites, it gets 0. And when you multiply reciprocals together, you always get 1. Okay, and then the distributive property, remember, is that whole business where if you have A times this bubble of B plus C, you can basically multiply the A to the B and also multiply the A to the C, and it's that. But this should not be a new thing, none of these properties really. Maybe the closure property was brand new to you, but all these properties, including the distributive property, should be familiar to you from things you've done in the past. And that does it for section 1-2.